So before we get started with actually talking about carbohydrates, I thought I'd spend a little bit of time reviewing stereochemistry nomenclature, and especially using Fischer diagrams, because we did introduce them earlier, but we didn't really spend much time with them. So let's start with what a Fischer diagram is. So let's imagine that you have a carbon in the center, and you have a CH3 going back like this. And then you have a CH2CH3 at the bottom, so that's an ethyl group. Okay, and on your left you have a Br, and on your right you have an H. So if the top and bottom groups are going backwards, then on a tetrahedral carbon, the side groups have to be going forward, and that's the orientation of a Fischer diagram. So the way Fischer would draw these is he would just go ahead and draw a cross like this. And then he would put H, Br, CH3, and then ethyl down here like that. And it was assumed that you knew that the groups on the sides were going forward. Now, if you wanted to assign a configuration to this, it's a little bit tricky, because what you would think about doing, at least initially, is going with the number 1 group, which would be the highest atomic number, bromine. The ethyl and methyl group are tied in terms of carbon. That's the atomic number of the carbon that's attached, but the ethyl group has a carbon attached to a carbon, so this would be number 2. And so we would be assigning the configuration in this direction. But if you remember, in the assignment of R and S, the hydrogen needs to be pointed in the back. So in fact, even though this looks like it's S, it's actually R, because when you put the hydrogen in the back, it'll be rotating in the other direction. So the same kind of mechanics apply to a Fischer diagram. You can still do the assignment, you can still draw the arrows like that, but you always have to remember this is going forward and that's going back at any given carbon. So this is the same method that we use for assigning configurations for various kinds of chiral centers in, I think, chapter 5 or 6. Now, when we're talking about carbohydrates, the types of structures you'll see a lot of, here's just another real quick example, are these. They're aldehydes and ketones, and you'll have to be able to sort of assign configurations to those, and it's a little trickier because now, for example, I have a CH double bonded O here. And then I'll have maybe like a hydrogen and then an alcohol group, and then I'll have a CH2OH. And so when you're looking at these carbons, well, number 1, by the way, is easy, right? Because it's the oxygen, right? So this is actually number 1. But which one's number 2? And the way you do the assignment is, since these two groups both are carbons, you look at the next atom bonded to it. The highest atomic number would be oxygen, but the way you treat a double bonded oxygen is as if this carbon was bonded to 2 oxygens, so the number 2 priority group would be this one here. Again, we're going in this direction. That's that looks S configuration, but this hydrogen is in the front. So that would be R, right, in terms of its stereo designation. So the next thing that you have to be good at is being able to rotate Fischer diagrams and not screw up the configurations. So for example, let me take this one that we just did up here, and then I'm going to turn it 90 degrees and let's see what happens. So in other words, I'm going to go like this, and then I'm going to rotate it in this direction. And so I'm going to put the CH3 here, put the Br here, I'll put the the ET here, and then I'll put the H up here. So I have 1 and I have 2. So look, it's going that direction still. So what would that tell me? Well, it looks like it's S, and then the hydrogen's up here. This is in the back. So now this becomes S. Remember, this was R. And the reason for that is when you rotated these bonds in this direction to produce the diagram that I just drew, you made the hydrogen go from the front to the back. And so that's actually not a thing that's possible with a carbon center very easily, just by popping it over in the center and pushing everything back like that, right? So you have to be careful. Now, let's say you turned it another 90 degrees, and so by turning it another 90 degrees, so I like to do this, and I'll just say 90, all right? Then what I'll end up with is this. So I'll have ET up here, I have H here, I have CH3 here, and then I have BR, that. And then if I look at this and I say, okay, is this R or S? Again, this is 1, this is 2, and you notice the rotation, it never changes, but the hydrogen's now in the front, so this is R again. So the combination is that if you turn it 180 degrees, that's fine. If you turn it 90 degrees, you've drawn an enantiomer of that compound. Or you flip the stereo, because we'll have lots of compounds with multiple centers. By flipping it sideways, you actually change the configurations of all the carbons in the structure. So rotations, let's put a little note here. Rotations 90. Let's just go with the compound we have. This is the enantiomer. And then you can also do 180, and that's the same. Now, you can switch two groups, as you remember from before. Switch 2. And that equals the enantiomer. You can draw the mirror of it. Oops, 1R. And that's also the enantiomer. So, for example, if I have, let's say, this, and I do the mirror image of it, so I draw a mirror plane, and then I just do ET CH3 H and BR. That would be the enantiomer, but I could also just switch two groups, and so I could go like this. I could have H, and it doesn't matter which two groups, right? So you can do this and ET, and that would also be the enantiomer of that compound. In fact, these two compounds, by the nature of stereoisomers, are the same compound. All right, so those are some of the things that you have to sort of practice or remember what you're able to do with drawing stereocenters using Fischer diagrams, as well as standard perspective diagrams. So let's start with what are carbohydrates. The origin of the name of a carbohydrate, you could take a look at, for example, glucose. You all are familiar with C6H12O6. If you break this formula down, it actually looks like C6H2O6. So it looks like a hydrated form of carbon. So that's where the name comes from, but there are a large number of carbohydrates, and we'll start with what we call the monosaccharides. Now, the word saccharide means sweet. Mono just means single unit. We also will be talking about polysaccharides and talking about structures of polysaccharides. And really what those are structures that are made up of various monosaccharides. So let's talk about the types of monosaccharides that you can have. You can have monosaccharides that contain ketone functional groups. And these are known as ketoses. Typically, the structures will look something like this. There are polyalcohols as well. This is the smallest of the, oh sorry, don't need that. This is the smallest of the ketose sugars. This is dihydroxyacetone. You'll notice that it has the structure of acetone, but it has hydroxy groups on the end, and then it's a ketose because it contains the ketone functional group. Now, there's also aldehyde-containing sugars, and these make, we'll call those aldoses. Aldose is for the sweet term. But aldoses contain an aldehyde functional group. And so a simple example of this, the smallest aldose that you can have would have a CH2 or CH and an OH, and then a CH2OH, and then at the very top it has a C double bond O and an H. So it's an aldehyde functional group. Let's see, here we go, like this. And again, it's a polyol that it has many alcohol functional groups in it. This one is known as glyceraldehyde. It's the smallest of the smallest of the aldoses. And so we have, by functional group, we can classify things as aldoses or ketose. Just double checking my spelling there. And then beyond that, there's a couple other things we can do. We can specify the number of carbons. So triose is the smallest of the monosaccharides. So we would have 3 carbons. So that's a triose. And then there's 4 carbon. That's tetra. So this is the same pattern you're familiar with. Then 5. This is pentoses, and then there's 6, and those are hexoses. Okay, so we can combine these terms, and so we can say, for example, this dihydroxyacetone is a keto triose or triose, and then this is a aldo. Glyceraldehyde is aldotriose. Glucose is aldohexose, so that would be a 6 carbon aldohexose is a 6 carbon aldehyde sugar. Now, let me draw for you a Fischer diagram for glyceraldehyde. So for glyceraldehyde, the way we would draw its Fischer diagram is, one way to draw it is like this. So CHO is the designation for the aldehyde functional group. And then it has a chiral center at the second carbon at C2 because it has 4 different groups on it. This is one isomer. And the other isomer, we could draw the mirror image, and that would be like this. Again, the CHO is not chiral, and neither is the CH2OH. But the central carbon could be mirror imaged like that. Now, we could, if we wanted to, assign R and S configurations to this. But what Fischer did when he did these designations is he went ahead and decided that if the OH on the second to the last carbon on the bottom is to the right, that this is D. And D is like dextro means to the right. Okay, it's different than the optical rotation, like dextrorotatory and levorotatory, but it comes from the same word. It just, in this case, it means the OH is on the right, and it's not in respect to what its interaction with light is. Okay, so the other one was called L. So this is L, glyceraldehyde. And this is D, glyceraldehyde. Okay, so we have D and L, and these produce the two major families of the aldose sugars, which we'll talk about at the end of this lecture. Now, if you look at glucose, glucose looks like this, and so it's got actually 6 carbons. The bottom is CH2, OH. The top is CHO. So in that respect, it's the same as a glyceraldehyde. And then it has 4 because it's an aldohexose. It has 4 other carbons in the middle. And each one of those can be represented in Fischer diagram form. So D-glucose looks like this. So this is D-glucose. And then like this. So that's D-glucose. Now, what do you think the mirror image of that molecule would look like, the enantiomer? Right? What does L-glucose look like? So I'm pausing for a second here myself, and I'll let you sort of stew over that and figure out what it looks like, and then I'll start the video. Again, you should pause and draw it, and then we can see how we compare. Okay, so I'm going to fill this in. When we talk about L-glucose, a lot of times what people will do by mistake is only flip the bottom stereocenter, but to be the enantiomer, the mirror image of it, you need to flip them all. So it is actually the mirror image all the way up the structure. Oops. So that would be L-glucose. It is the mirror image of glucose at every one of the 4 stereocenters. Now, just to be clear here, a little bit of extra terminology here. Oftentimes sugars differ from each other in their structure at a single stereocenter. So for example, if I drew this, and then I put CH2OH at the bottom and CHO at the top for my aldehyde, and then I put it like this. Oh. Yeah, let's do that. So what did I do? I took L-glucose and I made a new L molecule. This is L-allose. Allose as in they're all on the same side, and then the other sides are all hydrogens like this. Okay, so they only differ at 1 carbon. That 1 carbon is this one. So now when we number the carbons on an aldehyde, the way they're numbered is we start from the top. We go 1, 2, 3, 4, 5, and 6. So that's the same like nomenclature numbering that we use. They're different at C3. So L-glucose and L-allose are said to be C3 epimers of each other. And an epimer is a stereoisomer with multiple centers that only differ by 1 stereocenter from each other. So it's a 1 stereocenter difference, and we call those epimers. And then for the sugars, we say things like C3 epimer to indicate at which carbon they're different at. One other thing about sugars and numbers of isomers is, if you remember the rule that we had for number of isomers, it's always 2 to the n as the maximum number of isomers. And since we have 4 stereocenters for the aldoses, then what we can do is we can say 2 to the 4th. That gives us 2, 4, 8, 16 different stereoisomers. Of the 16 different stereoisomers, half are Ds and half are Ls. And in biology, and in human, the only isomer that gets used in the body is the D isomers, and the L isomers are relatively rare. The other thing to point out is to have more than 6 carbons does occur occasionally in nature, but the majority of the sugars found in nature are 6 carbons or less. So when we're talking right now about monosaccharides. So there's an individual sugar units. So, for example, glucose is a monosaccharide. Fructose is a monosaccharide. Glyceraldehyde is a monosaccharide. It's a single molecule of sugar. Now, when you put many of them together, this is when we get to the term we call polysaccharides. So we use some other terms, like we have like disaccharide. A disaccharide has 2 sugar units. So, for example, it could be glucose and glucose, for example. But it could also have 3, so that would be a trisaccharide. It turns out like after trisaccharide, and I'm not going to spend too much time on this, but after trisaccharide, anything from about 3 to 10, so this is actually 2, right, and this is 3, but 3 to 10 falls in this weird range they call oligosaccharides. But the word oligo itself means like a few, so it really is the word for 3, like from Latin, or just a handful. But we use it to mean like 3 to 10. So an oligosaccharide can have as many as 10 sugar residues, is what we call them. So these would be known as individuals, or called residues. And then if you have more than 10, just roughly speaking, that's when we really start talking about polysaccharides. Another classification we use has to do with the redox chemistry. And so, for example, silver ion can be reduced by glucose. So if I take glucose and I combine it with silver oxide, and this is done in a basic ammonia-like solution, and we'll get to that in a little bit. You can get the oxidized glucose, which is a gluconic acid. So it converts it to a carboxylic acid. So it goes from CHO to COOH. And then this is being oxidized. And then you are then taking the silver and reducing it to silver metal. And that's the reaction we typically do around Christmas time when we make Christmas ornaments. And this is also known as Tollen's reagent, which is used to identify reducing sugars. So the glucose is being oxidized. It is reducing the silver 1 ion to silver metal. I should point out the other term that's on this page is not oxidizing, it's non-reducing. So it's either reducing or non-reducing. So Tollen's test will not react with ketones because the ketones can't be converted to carboxylic acid. So that sounds fairly simple, but you have to be a little bit careful because in the ketose sugars, it's not a straight ketone. You have a ketone like this and an OH like this, And you also have OHs below, but these ones don't matter, so I'll just call them R. You can form enols with this, which eventually convert into aldehydes. So under basic conditions, there's a lot of aldehyde sugars and ketose sugars that will convert, because it's a base. Remember, enolization is base catalyzed. There's a lot of ketoses that can be converted over to aldoses under basic conditions through enolization. So basically the process looks something like this. So that's the formation of the first enol, and then it can convert over to this. So this aldehyde on the end and the alcohol in the middle, like that. And it can go back and forth, so you can actually have interconversion back and forth between, for example, glucose and fructose are very closely related, so you can get, under basic enough conditions, you can get interconversion between the two. And so fructose actually can show a positive test in a tolerance reagent, even though its pure structure doesn't actually have an aldehyde in it. Now, I'm going to be drawing a lot of sugars. And you sort of saw what I did over there on the right. I'm going to be using notation to simplify my notation for sugars. So, for example, this is glucose. And I'll draw what I drew before in the Fischer diagram. And I learned this, I can't even remember where I learned it. It was a long time ago. But it has 2 on the right, 1 on the left, and then 1 on the right. And I'll be going over how you memorize all these. I'm horrible at memorizing, but it turns out I can memorize these okay just because I know some tricks on how to remember it. It starts with mnemonics that you see at the bottom of the slide right here. So rather than drawing that, it turns out you could also draw this. Right? You don't need to draw the hydrogens, right? So you could draw OHs like this. And then CHO like that. And then CH2OH at the bottom. But then if it's a sugar, we know the CHO at the top for aldoses is always in the same place. And we know that the CH2OH is always at the bottom, sorry. And so you could also just draw this. I like leaving the CHO at the top. And that could also be glucose. And my laziest version of this is to simply put an O at the top to designate which end is the top and then go like this. And that would also be glucose to me because this represents CH2OH and this represents CHO. Now, you got to be a little bit careful because that's not a standard notation, but it does help you remember what the structures are. So if I was looking at fructose, fructose is actually this. There's a carbon here, so I'm going to draw it the first time. And then it's oops, I left something out. Let me just redraw that. It was just messy. I left one of my carbons out. Part of the reason I'm messing it up is because I'm not used to actually drawing the whole thing out all the time. So let's make sure I got 6 carbons here, but this should be fructose. So 1, 2, 3, 4, 5, 6. Yeah, so that's fructose. Fructose can be drawn like this. And then you can put the O on it if it helps you, because sometimes it gets a little messy. and then that would be fructose. So this is my skeleton key for fructose, and this is my skeleton key for glucose. And like I said, a lot of times I'll leave the CHO at the top, and I'll leave this group off the bottom like that because I know that's what's there. And for fructose, it's always CH2OH at the bottom as well, so I don't need to draw it either. All right, and you can see the close relationship between glucose and fructose and how enolization can cause those two to interconvert at these two carbons here. Okay? All right, so what I'm going to do next is I'm going to go through and I'm going to list out all the structures and how they're related to each other. And the way that I draw the structures is also related to how they're built, like synthetically. Okay, so we'll talk about those reactions in the next installment of this lecture series. There'll be 2.5 lectures, maybe 2 lectures on sugars. But these are the mnemonics I use. Get Raxol is for all the aldotriose to aldopentose sugars. So there's glyceraldehyde, erythrose, threose, ribose, arabinose, xylose, and lixose. And you'll notice that I have a whole separate mnemonic. Now, Get Raxol I learned from the guy who retired, I guess, about 4 or 5 years, maybe further after I started. And he learned this one in biochemistry, I think, from Princeton or something like that. So it's a well-known mnemonic, though you don't see it all the time. And then all altruists gladly make gum in gallon tanks. That one's been around forever as well. That one seems to be fairly well known. And that's for all the aldohexoses. Now, if you remember, we talked about there being 16. So these are actually just the D or the L. So there's actually 2 of each of these. There's D-allose and L-allose and D-altrose and L-altrose. But you'll notice there's 1, 2, 3, 4, 5, 6, 7, right? Because I left one out. The one that's missing is Aldose. That's funny. Glad I counted them. So that's Aldose. That's the in gallon tanks. Okay, so those that's the mnemonic. It's so funny. I didn't try to memorize it. I just tried to get it out of my head. Or I didn't look it up. I just tried to get it out of my head from memory, and I skipped one. So there's my 8, right? So this is 6 and 7 and 8. I'll just leave that in. I'm not even going to bother to edit. It's kind of funny. Now, but that's the value of a good mnemonic. It'll help you remember all the names, and then I'll show you how to remember all the structures, okay? And then the ketoses, I don't know mnemonics, so I came up with Dirk Psycho Friend sort tags, and that's D-erythrulose, ribulose, xylulose. You'll notice how closely those are related, right? To these, xylose, ribose, and erythrose. And if you look at the structures, you'll see that similarity. And then there's the psychose, fructose, sorbose, and tagulose. So I call this the sugar tree, and we're going to do the aldoses. And so I'm going to draw the first one, and then I use colors to help keep track of everything. I'm going to start from the top because, you know, the tree is smallest at the top. And I'm going to go like this. I'm going to draw glyceraldehyde. So I'm going to draw D-glyceraldehyde. So to draw D-glyceraldehyde, it's going to have a formula that looks like this. CHO at the top. Computer's getting really hot and slow, sorry. And then it's going to have C, and then OH, and H. Remember, this is the D sugar tree. The L sugar tree is just a mirror image of this. CH2OH. Now, the reason I'm showing you this, by the way, is I've had many students tell me the first thing they had to do when they got to their transfer school is they had to take quizzes that showed that they memorized the sugars and the amino acids. That was their first day of class. And so I think it's useful to go over this, of course, in a take-home situation or an online exam situation, pure memorization has not a real large component, but it is still valuable to be able to do this kind of thing. So in my simplified notation, that would be this. Okay, so this is how they synthesize sugars. Between C1 and C2, remember this is 1 and then 2, they insert another carbon. Okay, so the way it's actually done is they add a carbon to the top that becomes an aldehyde, and then this becomes an alcohol. So when you do that, then what you're going to end up with is the bottom part's going to be the same. I'm going to draw it way out here. And then I'm going to draw on top of that the next addition, which would be this. And then on top above that I have O, like that. So that would be one of the structures that you create. Now, when you have C double bond O, and you convert that into an alcohol, when a nucleophile comes in, for example, to do that, what ends up happening is this pair of electrons goes to the oxygen. But here's the thing, the nucleophile, because this is trigonal planar, can come from the top or the bottom, and you get a pair of stereoisomers out at that carbon. So what ends up happening is, I'll try drawing it like this because it's a little hard to draw that. You get this. That's the original one, and then on top of that you're adding this, like that. So the way I set these up is to have these guys pointing towards each other on the inside all the time. Okay, anytime you do that, or pointing away from each other all the time, but every time you add one, it's always pointing towards. So this is glyceraldehyde, D, because it's pointing to the right. This is D here, right? Oops, let me draw that back. So this is D-glyceraldehyde. And I'll abbreviate it there. And then this is erythrose. And this is threose. So erythrose, and oftentimes in organic chemistry we talk about erythro. That means the groups are on the same side of the chain. So this would be erythrose, or this would be threose. Okay, we say erythro and threo. Now, if I add another carbon to that, okay, so now I have this chain like this. I'm going to add another carbon. That next carbon adds like this, right? So what I have is I've added this, and then underneath erythrose I would have two. This next one would be drawn exactly the same way, but now the next one is pointing inward. So this is that from the synthesis, and we're adding to the carbonyl. We're creating an epimer, in other words, of the other compound, at C2 epimer of the other compound. So now let me go ahead and do threose's pair. I would have, again, I make them point inwards like this, inwards like this, towards each. Sorry, my headphone shuts off periodically. Goes like this. And so that would be the part that's added. All right? And so this is the Raxel part. So this is the get, G-E-T. So this is ribose, ribose, arabinose, xylose, and then I always I say lixose because it tastes so good. And then we make the next set. And so to make the next set, I draw ribose like this again. And then I add another one on top, pointing in the same direction. Like that. And you notice I'm not even drawing the O at the top because I think the orientation is understood. And then the pair, the C2 epimer of that is going to look like this. And what I've added is this here. And then I'm going to go like this. I'm going to do arabinose. So I'm going to go like this. And what I've added again is this guy. And so I'm going to go a little bit faster. And maybe you could pause and go ahead and do the remaining and then see where we compare. Okay, so if you paused it and came back, this is the rest of the mnemonic now. This is allose, altrose. So all altruists gladly, this is glucose, mannose, make, gum, this is gulose. Now, if you look at gulose, you notice it's like almost like glucose, but it's the letters are switched around, and there's not a C as well. But gulose, it is the mirror image of the inversion of glucose. So if you took glucose and flipped it over, and then took its mirror image, that would give you gulose. So all altruists gladly make gum. This is idose. For in, and this is galactose, and this is talose. Okay, so that's a simple way of, if you need to remember what the sugars are, having to memorize them is one thing, but to be able to recall what they all are is a skill that sometimes is handy when you need to like remember stuff. I don't know, maybe an MCAT or something crazy like that. Okay, so that's the mnemonic it's how the mnemonics are used along with drawings to give us the structures of all the aldose sugars. Okay, so what we're going to do is start, and I'll show you how to do the ketoses, and I'll have you guys sort of fill it in, and then I'll pause the video and then come back and you look to see what I drew. But to start with, ketoses are a little bit different. We had a lot of different stereoisomers for the aldoses. We have fewer for the ketoses, and the reason why is because the carbonyl in the smallest of the ketoses is in the middle, and there are no stereoisomers of it. So dihydroxyacetone is achiral. Now, when we add our first OH group, it inserts here. So we go down one, and we go like this. And I'm going to do the abbreviated notation like that. And then we go like that. And this is the next sugar for the ketoses, and this is erythrulose. So it has just the one stereocenter, and it's the one that we assign D and L to. So there are L sugars. I'm going to just draw it way out here. There's a whole separate tree for these. Okay, these are L, and this is D, and I'll write the name here, D, erythrulose, like that. So L-erythrulose starts the whole branch for the non-D sugars, the non-natural sugars, the ones we don't see as often. Okay, and then we can start our pattern. So now the next one inserts here. So it always inserts underneath C2. So we're going to go down here, and we're going to branch out over here. And they're all going to be based on erythrulose. So I'm going to have a branch and a branch and a ketone like that. So go ahead and draw the rest of them. And then when you start, the whole thing will be here, and we'll go over it. So here's the rest of the sugar tree for the ketoses filled out. And some of the things you should notice, I guess, that are helpful to know is, for example, when you look at ribulose and xylulose, and you go back up to ribose and xylulose, you notice the bottom two carbons are of the same configuration, both to the right or right and left, right? So they're the first two in that branch. So ribulose and xylulose are similar. Now erythrulose, when you look at erythros, it's also pointing in the same direction. So they have those things in common with the structure, and therefore the names are similar to each other. And hopefully you got the hang of that and were able to draw those out. And I would say that's something worth practicing at some level in order to become proficient at doing it, so that later when you have to remember it, it won't be hard. All right, next, chemistry of the sugar monosaccharides. Many of the reactions that we're looking at are redox reactions, and so you can do hydride reductions. So, for example, borohydride or lithium aluminum hydride. When you do a hydride reduction of a sugar, it follows the same mechanisms that you've learned before. So let's take glucose, for example. So we'll draw glucose like this. And then I'm not even going to put the OHs on it. First step is sodium borohydride. And the second step is usually water workup to release the O minus from the sodium and the complex ion, and then that gives us this. And at the bottom it's still CH2OH. This is what's known as a polyol. So a polyol is a polyalcohol, has many OH groups, so each one of these is an OH. These, it turns out, have, oops, sorry, that wasn't glucose. This would have been glucose. Many of these polyols are also sweet, just like the sugars are. Their structure is similar enough to sugars that they retain their sweet component, but they're not usually metabolized, so you get no calories from those. So this would be glucose, and this would be glucitol. Now, glucitol can come about several different ways. So what I've shown here, so that's a hydride reduction. glucose produces glucitol, but it turns out L-sorbose can also give us glucitol, and let's look at how that is real quick. L-sorbose can also give us glucitol, and it looks like this. So sorbose, L-sorbose would be, well, sorbose is this actually. Let's just do sorbose first. And then you do the reduction. Oh, we want, and so this is D-sorbose. And then we'll draw L-sorbose, just so you can see this process. L-sorbose is the mirror image. Now, you don't have to mirror image the top group, and you don't have to mirror image the ketone as well. So the ketone is not asymmetric, but then everything else is flipped. So this would be L-sorbose. And then you can reduce that. So I'm just going to go like this. But that's sodium borohydride, for example, and water. And then you'll end up with this. And this. You get two compounds out. Because remember, where the ketone is, where the carbonyl is, can create two different stereoisomers. So one will be, what did I do? I started drawing the mirror image. Sorry, my bad. One will be like shown here with this one here, and the other one will be like this. Okay, so now if you take this compound and you flip it over, now let's reduce glucitol to its key structure. If you take this and you flip it 180 degrees, that is, you flip it over, you'll get the same molecule. So it turns out when we have these sugar alcohols, is what we call them, polyols, there's a lot of ways to get them from known sugar structures. So glucose can give us glucitol, sorbose can give us glucitol, and that's in fact what we call sorbitol. So there's two names for glucitol, and one of them is glucose and one's sorbitol. And if you look at like your chewing gum, sorbitol is one of the sweeteners that they're adding to gum these days to improve flavor, but also to cut calories. And it turns out there's some evidence to show that chewing gums like that reduces your tooth decay, because even though it tastes sweet, your mouth salivates and the bacteria can't consume it to produce plaques on your teeth. Well, it turns out if you take fructose, just to show you all these permutations. So fructose looks like this. You can produce glucitol as well. That is, you can do this. Hang on. I gotta get my mirror images all straight here. This, or you can do this. And you see, if you flip this 180 degrees, that gives us sorbitol. But you can all just go up to here and compare between here and here, and it's the same structure, right? So it's a little tricky with these sugar alcohols, knowing how they're all related to each other. Usually on a test, I'll ask like which of these sugars can produce, and then I'll just randomly pick like a glucitol or a mannitol or sorbitol, and then you have to recognize that some of these are the same and some of them are different. Okay, now this is mannitol, is what the name of this is. And mannitol is another one of the artificial sweeteners. So if you take mannose, right, that implies that if you take mannose is this, and you reduce it, that you produce mannitol. So fructose and mannitol can give you glutatol as well as sorbitol as well as glucose. Anyways, yeah, it's complicated. Well, it's not complicated, but there's a lot of permutations. Now, there are two general classifications of oxidation reactions that are used with sugars. We call them mild and stronger, or mild and strong oxidation. And so if you take, for example, glucose is just a simple one to remember, and you subject it to mild oxidation. So that's Tollin's reagent, or you could do bromine water as well. That's Br2 in water. So this is Tollin's. It's got ammonia and other. The way it's prepared is with sodium hydroxide, ammonia, and silver nitrate. But it's easier just to write Tollin's reagent. What you'll get is you'll get this. And this is an aldonic acid. And Bruce has a very nice way of remembering it. He says in an aldonic acid, one end is oxidized. In fact, I always used to forget, and when I read Bruce's little thing on it, I'm like, yeah, of course that makes sense. And then there's the alderic acids. And alderic acid oxidation is usually, to form an alderic acid, is you start with something like glucose again, but any of the aldoses. CHO. And it's nitric acid. Nitric acid is a slightly stronger oxidizing agent. Oops, nitric. And you'll get this. So in an alderic acid, both ends are oxidized. So alderic both ends are oxidized. So this aldonic acid would be called gluconic acid because it's the aldonic acid, and this is glucaric acid because it's an alderic acid. So hopefully that made some sense to you. Oh, and that's it. There's a bit more chemistry to cover, but we'll save that for the next lecture.